Is it because All right, so hello everybody. We're about to start now. So if you're here, please turn on your cameras. All right, so today actually I'm going to we're going to pause talking about experiment for a second or like for a day, and back to talking about statistical tests which are related to experimentation. So I paused. If you remember, last week we were talking about statistics. This week we've been talking about experiments. And so this part would involve how you look into how you could examine experimental results. And so that's why you needed to have like an idea of what experiments are looking for, which are differences, as we said, between or among conditions. And so it's then useful to talk about inferential statistics after you understand what experiments are all about. So some like some recap or like some review. So we mentioned that if you have a normally distributed data set, and this could be the case, could be not in any given data set that you have. We said that if you center the mean on 0, so imagine that the average is 0 just for the sake of simplicity, right? You would then have one standard deviation plus and one standard deviation minus. And like as we mentioned, standard deviation is like how an average score is deviated, has deviated from the mean score. And so we said like 68% of the data would be within -1 and +1. 95% of the data would be between -2 and +2, and around 99.7 would be between -3 and +3, right? And so that's like a normally distributed data, right? So if you imagine like we're measuring the amount of donation people gave to a donation call. Let's say the average was 0. So 0 in this case is, the average was $10. So assume $10 is 0 right here. So like the one in the middle, not below, not above, right? That would mean 68% of the cases would donate between $8 and $12. So yeah, like one standard deviation is 2, so $2. So one standard deviation plus is $12. One standard deviation minus is $8. In 95% of the cases would be between $6 and $14, and 99.7 cases would donate between $4 and $16. So if you take that as a whole, so if you look at in the both ends, right? We would see only that basically about 0.1%, not 1%, but 0.1%, or like 0.01 on both ends either donated below $4, so let's say $1, $2, $3 or nothings, or above $16, right? So those again, so those are people who are not included, obviously not in the 68%, but they're not even in the 99.7%. They are more than either to the negative tail or the positive tail, right? What do we call these cases, by the way? We've mentioned like there's a name or a label for them. What do we call cases on like the end tail of both ends, the positive and negative? Do you remember what we call them? So cases that fall beyond the normal distribution, we call them.
They called outliers.
Outliers, you're right. Yeah, they're called outliers or extreme cases. And that means they don't follow, like, they are not falling within even the normal distribution of the specific samples. In other words, those outliers, they are outside this herd. They are unique cases. So there are something specific about them that made them stand apart, okay? So hold on that thought for a second. Right. And so imagine now we're going back to statistical analysis of specific hypotheses, right? How do you know that, for example, like a group of participants or a group of like sample subjects are different than the population, right? So let's say outliers in terms of like physical activity or like academic achievement or like communicative abilities or enjoyment, right? Or proficiency in first shooter games, you name it. How do you know that those people, individuals, population, etc., are different than your average population? And the answer is we estimate, so similar to what we discussed, we estimate if the range that those participants are different than or standing apart from the range of the rest of the population. Okay. So we would know, in other words, how like a group of cases is different than the normal population. So normal here just in a statistical sense, right? And that doesn't have any like another connotation, just in a statistical sense, right? How will we know? So the answer is we estimate what are the parameters of the normal population, right? And of those cases stand apart, we can say they are statistically different, or statistically, there's a statistical significance, right? And so here to give you an example, so we are looking into like scores of students on a given test, right? So the test is out of 50, by the way. Here's the list of students you could see right here. So this is the list of students, and here's their scores or their points, right? So as you can see, mean scores. The sample would contain 26 students, but those students, so they're coming from a population of similar students, right? So they are all coming from the same class or the same section, or the same college, same year. We would then, so we want to know if a different group of students, so a different group, would be different than this group right here. And since these students are coming from a population, there are possible ranges of what mean score could they've gotten, right? So in this case, so there's a typo in the slide because there was like a different slide. But here the mean score is 42.7. Assuming we have the same like differences between the students and their clustering, so the standard deviation is the same. What possible mean scores they could have landed on if they took the exam multiple times, right? Because remember, we said in a previous lecture that if one like random change happened to one student, so this person right here got 39, if they ended up with like 42, right? The average here would have been pulled up a little bit. So it could have been 43, right? So if two students, if this person here get 50, this right here could have like 43.1 an average. Similar, and the same is the opposite way, right? So if just one student screw up, for like lack of a better word, like they got like 42, just one student, right? That will pull down the average. So in other words, if we account for random variations, remember when we say that about sampling, like, yeah, you sample one population. So to what extent, to what extent do you, are you excited about taking the vaccine, right? If we sample from the same population, the average could be sometimes 4.9, sometimes 5.1 out of 7, and sometimes it's 5. So that doesn't mean those samples are different. Those are just random variations, right? So that's we want to know. We want to see, okay, if the differences are due to random variation from a different group, or there is a systemic difference. So if we recall the things about we said about the sampling error or something like, if we get a group of students and then they were systematically picked because they are better performers, how can we see this from comparing the two data sets? That's the point, right? And so here is what it says. Here's how you do it. We would draw what we would call the confidence intervals. All right. So the confidence intervals are the limits, upper and lower, and please, by which we say anything that fall between those two limits would be considered just a random variation on the same population, right? Anything that fall outside those two limits would be considered a statistically different population or subpopulation, right? So, and again, population here in a statistical sense, so doesn't mean the American population or Chinese population. They are in a social sense, yeah, the same population. But what we mean here by statistical things, so population that share the same characteristics, right? So if they fall outside the limits, we would say, yeah, it is a different subpopulation with a unique characteristic, right? So in other words, so you have here a mean score. Let's say this is the mean score that one class, so this was the class average they got like in high school, 4.27, right? The upper limit for that, assuming like, I'm going to talk about how you would calculate the confidence intervals. The upper limit is 5.62, the lower limit is 2.92. Any group that fall here or here would be considered different, right? Anything here is same, i.e. anything here would just be considered like a random variation, right? Any mean score that fall here would be considered random variation from the same population. How do we know? So how do we calculate the confidence intervals, right? So now you're asking, what are the confidence intervals? So remember going 2 slides back, we actually calculate something called a standard error, which comes from the standard deviation. And I'm going to show you the formula in the next slide. But basically, the confidence intervals are 2 standard errors, which will get you into 95% of the cases, if you remember. So 2 is 95%, and 3 is 99%. So 95% is like if you're relying on 2 standard errors as your confidence intervals, and 99% if you're relying on 3 standard errors as your confidence intervals, right? And so the standard error, so if you going back, so the standard error comes from the standard deviation. So let's go back to the standard deviation. If you remember, I said if the standard deviation is lower, so if you have a low standard deviation, that means the cases are more clustered around the mean. If you have high standard deviation, that means the cases are spread apart, right? And so that standard error is relying on that, which is coming from the sample size. So the higher the sample size, the lower your standard deviation would become. That's just like a natural growth, right? So imagine so if you just take, let's give a simple example. So if just I randomly pick 5 students from your class and look at their exam scores, they could be all over, right? So because I could have 2 people who did really well, 2 who did really poorly, and 1 average. So the standard deviation would be very high, because there's like huge differences between each case and the average, right? Either plus or minus, right? So the larger my sample is, so I've taken all the students of COMM-265 across different sections, we would have a more like, yeah, you could see a true mean with cases clustered around it. So the largest sample size, the narrower the intervals would become. And the standard error is then is how the sample mean is estimated to deviate from the population mean, right? So if you have different samples from one population, how is your group average score is different than the population's average score, how far it is. So we call that the standard error. So if you remember, this is very similar to the standard deviation thing, right? Because we said standard deviation is how an average score is deviating from the mean score. Standard error is basically the standard deviation of standard deviations. That is to say, how the group mean score is deviating from the population's mean score, right? And how do we then, like, so you would ask the question, how do I know what the population mean score? If we just said 3 weeks ago that the whole point of doing a sample is because we cannot realistically survey the whole population. So how do you say now that there's something called the mean and the population mean score? The good thing about it that this is just an estimated thing, right? So standard error, and this is, by the way, so the good news is statistical software will just calculate the standard error easily for you. So you don't have to do math by yourself, but you need to understand where it comes from. So the standard error is basically is the mean score divided by the square root of the sample size, right? And the idea is the larger your sample size is, all right here, the more the mean score would resemble the population score, right? Up to the point that if you have a full census, then the mean score of a sample is the mean score of the population, right? But the standard error means saying, okay, we adjust the mean score. So this is like a Greek for mean. We adjust the mean score according to the sample size, because a small sample size obviously there's a larger room for error from the population, and the larger the sample size, the lower the standard error should be, right? So imagine here, like we have, this is the example I give. We have a sample of 5 students. Their mean score was 17, right? We so 17 divided by square root of 5, standard error is 7.6, right? So that means because this sample is very small, the population mean score could be, so this is 1 standard error, right? 7.6. If we do 2 standard errors to account for 95 of the population, 2 times 0.76 is 15.1, right? So in other words, the population mean score could be 15.1 above 17 or 15.1 below 17. So it would be somewhere between 1.9 to 17, 15. That's like 38.1, something like that, right? And so that's the thing, right? So those are the confidence intervals. Anything that any change within the confidence intervals of the standard error, we would call that just a random variation due to sampling. Remember that, due to sampling differences. Remember when we mentioned sampling error versus systematic? Anything that's go beyond two standard errors or above the mean or two standard errors below the mean would be considered statistically different. Now, how do we translate like why do we care about all of this, right? If we want to see if we want to see, for example, that like how something could be predicted. So we mentioned about opinion polls, right? So if you want to see how people would vote, right? Remember that. If you have a larger sample, you would estimate the average scores in your poll would be closer to what with the election results would end up being, right? And so you need then to have, you want your standard error to be smaller so the confidence interval could be more precise, right? And here you can see an example, right? So the standard error comes from the standard deviation and the population size. So if you have here larger standard deviation, small sample size, you have here a very large standard error. Because think about it, if you have a very large standard deviation, that means your individual results were all over the place, right? And I like to give an example of grades because something we can easily imagine, right? So someone ended up with 100, like few people ended up with 20, other people ended up like with 50, others were at 80. So in other words, the results were all over the place. That would end up giving you a huge standard deviation score, which would then affect the standard error. So we have a high standard error. So the confidence intervals here, if we take two standard errors, they will be like around 20, 9.9 plus 9.9, which is huge, right? So your confidence interval would be very, very far from each other, right? You have small standard deviation and a small sample. So yes, the sample is more cohesive. So the results are close to each other, but the sample size is still small. And so you will still have like a significant standard error. So 2.4, right? What you want is to give you better results is like a sample with small standard deviation and large sample size. So I could see that, okay, I took a look at the results of all 200 students who took communication methods, large sample size, and their results were close to each other. All were somewhat, on average, close to the mean, so low standard deviation. And so I end up with a very small standard error. So this means that the confidence interval would be very close to the mean score, right? So standard error times, if it's 95%, again, it's 2. If it's 99%, it's 3 standard errors. So that's the thing you would remember, right? Let me then, okay, I'm trying to go back. All right. So yeah, basically the confidence interval. So we explained how you calculate it, but the confidence interval, so something that you would read in research papers, especially with experiments, they would tell you that we measured the significance or like the test at the 5% level or the 1% level. So 0.05 level confidence, that's called the confidence level, or 0.01 confidence level. What they're simply saying, this is not very complicated, by the way, is that 0.05, that means it's about 2 standard errors confidence intervals, right? When we say, yeah, this was significant, this group was statistically different than the other group at the 5% level, that means they fall either above, so the 95 or below the 95, right? So they are talking about the 95%. So this scores, in other words, fall beyond the 95% of the cases or the range of possible scores. If they say it's at the 1% level, that means they actually had a more rigid test and said, okay, this group or this case doesn't only need to be 2 standard errors above or below the mean score, they actually need to be 3 standard errors. So the confidence intervals were drawn at the 99% level and not the 95% level. So to give you back right here, right. So the upper limit and lower limits, they were not, so this is at 95. So you could see 2.5 here, 2.5 there. At 99, you would actually draw your confidence intervals right here, all right? And you would say the group mean score need to fall either here or here to be considered out of the limits of the normal population, okay? And so, by the way, 95 and 99, this is like, this depends on the choice of the researchers and the reviewers. So if you think 99 is just more rigid than 95, just to make sure that, yes, this group is very, statistically different than the population, right? So, how does that relate to group or comparisons of experimental groups or condition, right? Now, take a step back a little bit and think of this, right? So we have 2 groups. So we were doing, let's say, for example, a research on the effect of advertisement on sending donations, right? Okay. So group A saw one version of the donation advertisement. Group B saw a different version. Each group will come back with a different mean score, right? So assuming the maximum you could donate is 100. So one group ended up donating 20 on average. So the average score of donation was $20. The other group was 25, okay? And we want to say, okay, was 25 statistically and significantly different than 20? So obviously, nominally, right, 25 is different than 20. But the key is 25 just a random variation from 20 due to sampling, right? Or is it systematically different than 20? So you see, that's why we do the confidence interval, right? And so we want to say, okay, if we look at group A, we get the mean score, we calculate the confidence intervals, right? So the confidence interval, again, are drawn from standard error, which the standard error is drawn from the standard deviation and the sample size, right? So if we say, okay, let's see a standard error of 2 points above and 2 points below, 2 standard errors plus, 2 standard errors below, and see what's the possible range of mean scores of the population in which this group was drawn from, right? So we are adjusting for standard error. And so when you compare 2 groups, okay, we're not looking into the mean scores only. We're looking at the mean scores with their distributions. And this is a key part. Remember, remember the example we show you, like two columns of different students giving score. and one had a slightly different average. But if you actually looked at the individual scores, you could see that, okay, only one student made that difference in the average, but the distribution was basically the same in each group, right? That's what we mean by statistically significant results. And so I know this is a lot, so I would show you then in with an example, by the way, I showed you how to do t-tests, but just to demonstrate what we mean by confidence intervals and mean scores and statistical difference. I'm going to now stop sharing the PowerPoint slide and I'll go to Jamovi, and I'm going to show you like a concrete example so the issue becomes more clear to you, right? So let me go here. Okay, so I'm trying to exit. Okay, share screen. Sorry, I have too many screens open. Okay, where is Jamovi? Here we go. Okay. Right, so I'm going to do this again, right? So you get the, so we want to know if two groups are statistically different than each other, not in a sense that the mean scores are nominally different, but the distributions are also different. So if we take like a cluster, if we look at the distribution of group B, it will fall outside the distribution of group A, okay? So here we have a dependent variable, which is likes. So this is the same data set that you have, guys. The one about the tweets from the donut place. So I'm still using the same data set, right? And if you could see here, so here's the number of likes, and we want to see if the number of likes for posts during the weekday are different than the number of likes for posts during the weekend. So Sunday and Saturday versus weekdays, right? So here we want to see if group 1 or group A is different than group 2. So we would look at the mean difference here, and please, yeah, pay attention to, I'm going to explain the number, right? And so I'll look first at the group descriptives because this would be easy to read. So we have 181 tweet in group 1 and 26 tweets in group 2. So 2 is weekends, 1 is weekdays. Mean score for the weekend is like 6.58. For the weekday is 5.65, right? But then look at the plot right here, okay? So this is group 1, and this is group 2, okay? So this is the mean score right here. Mean is the circle, and that's the one we're looking at. Confidence interval is this one with the blue, right? Now, I'm going to ask you a question. Look at the mean score of group 1. Does it fall within the range of group 2 or outside the range of group 2?
The mean falls inside the range.
Right. Okay. Yes. So it falls, yeah, it falls within, yeah. So this right here, you can see it fall within this range, right? Okay. What does that mean? If it falls within the same range of the other group, what does that mean? Anyone guess? Based on earlier slides? So these confidence intervals, by the way, are coming from those standard errors you see right here, right? So one standard error is like 0.40. Two standard errors are 0.80. So the confidence intervals is like 0.80 plus the mean, okay, and minus 0.80 below the mean score, right? Okay, so could someone calculates what's if we subtract then this is time 2, by the way, so it's 2 standard errors, right? So it would be like 1.6. So I calculated that for you. So 1.6, right? So what is 1.6 minus 6.6? Oh, sorry, 6.6 minus 1.6.
5.
Right, it's 5, yeah. Right, it's 5, okay? So here, the lower range is 5. So this is 5 right here, okay? What is 1.6 plus 6.6?
8.2.
Yeah, 8.2. So this would be right here, okay? Right. So what this plot is showing you that anything between 5 and 8.2 would be considered within the normal distribution of this group. So any fluctuation between these 2 points would be considered a random fluctuations and not a systematic difference due to just the sample size and the standard deviation, right? And so because here, we could see that, remember, the sample size is very low, right here, so 26. You could see how wide the confidence interval is, right? So if a different group had any score between 5 and 8.2, it would be considered falling within the same range of this group, and not as a different group, like statistically speaking, right? So based on that, we would actually say that those two groups are not statistically different. To get that point, right? So because, yeah, you didn't fall outside the range, you fell within the range, you would be considered part of the same public. And then yeah, let me then scroll back here. Let me actually erase this, okay. This is in order to know where the scores fall. It's actually, we'll look at what you see here, the p-value. So here the statistics show you like, so this is 1.16, that's the difference. So that's 2 standard, like here. So the mean difference between the two averages, the mean score of 1 and 2 is almost, yeah, so minus 0.9. But the p-value here is 24 or 0.24 or 24%, which is saying, in other words, 24% here is saying the score did not fall outside the confidence intervals. It fell within, because remember, it's saying that if it falls within outside 2 standard errors, that's 5%. If it falls outside like 3 standard errors, that's 1%. So to translate this again, 100% minus 25 is what? 100 minus 25, what is it?
75.
Yeah, 75. So here I run it up. So 247 is 25%. So the main score of group 1 actually fell at the 75% of the distribution of that distribution of scores of here. So this is here, this line right here is at 75. And we want it actually to fall outside the 95%, right? So at the very 5% at the very end, so to fall outside 2 standard errors from the mean score. Okay, and because it fell within, they are both considered coming from the same population and not two different subpopulations. All right. How do we translate that into from statistical language to just an explanatory language? What this is saying in here that although you see two different mean scores between group 1 and group 2, this difference could be just due to random variation. Remember that? So yes, this one got higher average score, but that's just random. Because based on the distribution of group 1 could end up with this mean score or even higher or lower, right? So it could be, in other words, because we're looking at tweets, it could be that a few tweets could have changed the outcome randomly. So if we took a sample of different tweets from weekday and a sample of different tweets from weekends, we could see like the same mean scores of likes. Okay, right? So because this one, and the reason is we cannot tell if those two groups are different. It's like what I mentioned. The confidence intervals are too wide because the sample size is small and you have like a significant standard deviation. So we cannot tell for sure that this group is characterized by producing more likes than the other group. So I hope that illustrates like the point, right? Once you have two mean scores that are different, falling outside the confidence intervals of each other, then yes, you can say definitely this is, well, sorry, not definitely, but at least a 95% confidence that those two groups are statistically different. And so that's what I have for today. And you have the homework or the assignment for those of you who need to complete it. So if you have 4 assignments, you do need to do it. If you still have assignments to do, you would work with different data sets and you would conduct a t-test and ANOVA. And I think if you do that one, it will become clear to you what we mean by two mean scores falling outside the confidence intervals of each other. Because they will clarify to you, yes, so the distribution of one group is different than the distribution from another group, as well as the mean scores are different. Do you have any questions?
Just to confirm, those who have already done 4 individual assignments won't have to do the next one?
Yeah.
Okay.
You don't have to, right? You don't have to.
Okay, thank you.
If you do the 5th assignment, though, is it extra credit or no?
No, it's a 15 point. It's actually it's easier than the other assignments, to be honest, because you would follow steps on Jamovi and then the results going to be the same. And so yeah, but it's like a 15 point, and it should not take you long, by the way, because the videos I posted, I have different videos that show you how to do the steps. So if you just follow those, you'll be all good.
And then I just had a quick question, kind of following up on Jalissa's. For the individual assignments, was the sidecar donut tweet like versus dislike, was that considered a individual assignment?
No, that's just participation thing.
Okay.
Yeah. All right. So there's no further question, and yeah, take care, and I'll hope to see you.